Okay, let's see. Start broadcast. So we should be able to. Perfect. There we go. Okay, so let's continue with what we were doing yesterday, which was a naming workshop. So I'm gonna put molecules on the screen, and I'm gonna give you a second to work through them, following the steps that we learned yesterday. And then you will tell me their name, or you can just pause the video. And yeah, okay, so let's see. So right here we have a molecule that is very, very long, right? I'll give you a second to pause. 3, 2, 1. Okay, so let's dive into it. Our first rule is to find longest parent chain with functional group. Okay, so our functional group here, there is no functional group, right? But we know that we must have to include this alkene because this alkene is important. And so in order to do that, we must include it, and we would want to number it so that the alkene is on the least or smallest number possible. Let me make sure I'm having my voice on. Hello? Hello? Yep, it's on. Okay, so now let's see. This would be, you would want to number it, so we'd go 1, 2, 3, 4, 5, 6, 7, 8. Or we could have numbered it 1, 2, 3, 4, 5, 6. Nope, that's too small. 1, 2, 3, 4, 5, 6. Yep, this is the longest parent chain. Oh, wait, let me see. 1, 2, 3, 4, 5, 6. Again, too small. So yeah, this is the longest parent chain. We found it. And what is an 8? It is a octane, but because it has an alkene, it would be octene. Octane becomes octene because of alkene. And then we ask ourselves, what is a stereochemistry? Well, there's not a lot of chiral compounds, but we do see an alkene, so we know it could be cis, trans, or ZE. Let's see which one. They are big groups on the same. This is whenever it is opposite carbons or different carbons. I shouldn't say opposite. Different carbons, same carbon. Are big groups across the alkane in different carbons or the same carbon. So what I mean by that, it's like, let's see our alkane right here. Oh, sorry, alkene right here, right? Our alkene right here are the big groups that are attached to it. So we know this is a carbon, this is a carbon, they are double bonded. Are the big things across this double bond on the same carbon or on different carbons? Well, we see there's a big thing right here because, again, so let's imagine it for a second. This carbon right here is attached to a methyl and a hydrogen, right? This carbon right here is attached to this big old thing and a hydrogen. So when I ask you, are the big things on these carbons on the different carbons or on the same carbon? You will say, well, the big things is this, and then the big thing is this, right? Because the hydrogens aren't big things. Hydrogens are low hydrogens. So you're not gonna think about the hydrogens as big things. You're gonna say, this is the big thing, this is a big thing. Okay, are they on the same carbon or different carbons? They are on the different carbons. So we know that we are gonna not use the Z or E terminology. We're gonna use cis or trans. So now we ask ourselves, are they on the same, like facing the same way, or are they facing opposite ways? So something that is trans, something that is trans will look kind of like this. Like, you know, they have opposite ways. And that's kind of how this looks. Cis would look like this, the same way, or like this, same way. So what I like to think about is my little hands. I'm like, am I gonna put my elbow out like this, and then this is my head like that, or would it be? I don't know if that makes sense. But if I were to be this molecule, try to imitate its shape, how would it look? We can tell it from right here. It is on different carbons and they are on different size. That is a trans molecule. Okay, so then we go ahead, we put, for stereochemistry, it is trans, and then we already have the parent chain, so now we have to start numbering the substituents. So let's see, we have, what do we have here, the substituents? Three, yeah, four ethyl, four ethyl, oh, substituents, four ethyl, five methyl, and then that's it, right? Yes, perfect. And then of course we have our two ene, which is our alkene. Okay, so now we're gonna put all this together. We're gonna have trans, and we have to number these by what's it called? This is by alphabetical order. So E comes before M, right? So it's gonna be trans 4 ethyl. And then this part, unfortunately, does not count. I just wanted to make sure that we remember to number it. So maybe you can even put it over here, oct 2 ene. That way we know we don't have to put in the substituent parts because it's not really a substituent. We just have to remember to include the ene. Okay, trans 4 ethyl, 5 methyl. Oh wow, this is gonna be a long name. I'm gonna zoom out. I'm gonna move this over here. Let me erase this ugly blob. Blah 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 blah. Hey. There we go. Trans 4 methyl 5 ethyl. Oct 2 ene. That is the name. Perfect. Okay. You ready to move on? Let's go. So now I'm gonna put another molecule on board and I'm gonna drink a little bit of my tea. So that's gonna be your pausing moment. There we go. OH. Okay, so did I draw too many? 1, 2. Oh, I did. Oopsies. There we go. Take a moment. Okay, ready? So we have to find longest parent chain with the functional group. So off the bat, I would have been like, oh, this is longest parent chain, which it looks like it, right? However, we need with the functional group, which we can see our functional group is right here. So we'd say, okay, well, I don't want to do this because that's really short. Let's start over here. 1, 2, 3, 4, 5, 6, 7, 8. Or not 8, sorry. We don't count the alcohol. It's a 7. That seems like the longest parent chain. So let's go ahead and number it. And remember, we would want our branching at the lowest number. So we're going to extra branch this way. This is 1, this is 2, this is 3, this is 4, 5, 6, 7. So that is a heptane. There is no ene or ine. So we're going to keep it as heptane. Then we're going to see is this RS, what else? RS cis trans. But I don't think there is a chiral center. So we don't have to do that. And there is no alkene, so we don't have to do that either. Okay, so perfect. Next thing would be, so we have 1 ethyl, 2, sorry, yeah, 2 ethyl. And so remember, when we have two of the same, we just say 1, 2, diethyl. And then we also have this functional group, which is going to change our parent change to no. I don't know if you have to hepta 1O. I think we would. Oh, wait a second. Oh, did I mess up? Oh my gosh, yes, I did. Wow. I did not even realize that there is a longer parent chain. Wow, okay. So this is the importance of maybe not rushing through it, of being the first step, which is numbering to get it absolutely right. So we said we'd want the longest parent chain that includes an alcohol. And if you had paused it and you got it, amazing job. I did not catch this. So this is part of, oh, did not mean to do that. This is part of the longest parent chain, but it's not the longest parent chain. I should have included all of this because all that matters is that I include the functional group, that I don't leave it out. So yes, this was not going to ever be the parent chain because it does not include that functional group. It has it as a branched, but this includes that functional group and has a parent chain. I mean, an even longer parent chain. So let's go ahead and renumber it. Oh, it's going to be really hard erasing these tiny little numbers, I think. There we go. So it should have been 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Not a heptane. That is a nonane, which becomes nonano. And then don't have these substituents. We only have 3 all. So we can say that it's going to be no, put this up here. No, nah. 3 all. Oh. And then, let me resolve this. What else? Oh yeah, our 4 ethyl. Perfect. All right, so we have 4 ethyl, nona, 3 ol. Thankfully, we just have to bring that together. There's no other substituents. There's no like worry about chirality or alkene, whether cis trans, none of that. Nona, 3 ol. And that is our answer. I know that was a little bit confusing. At least it was to me. If you got it, amazing job. I have to get my noggin working. All right, let's try one more before we move on to different topics, because I feel like you may have enough tools in your toolkit to at least get like 85% of this right, of naming right, or be able to, like, especially if it's like a multiple choice or if they provide some more clues, anything like that, be able to deduct. And I also trust that you pick up things very quickly. So I'm sure that you remember a lot of these strategies. Okay, so first thing we have to say is find the longest parent chain with a functional group. So we're going to include the alkyne. So let's see. I'll give you a second to pause. And let's go. Okay, so we could do 1, 2, 3, 4, 5. Okay. What about 1, 2, 3, 4, 5, 6? There goes a longer one. And then 1, 2, 3, 4, 5. So it's gonna have to be this, right? That is a hexane, but because it has a ine, we're gonna say hexane, and it is at the, we're gonna have it at the lowest substituent, so we can say 1, 2, 3, 4, 5, 6. Hex 2 ine. That should be correct. Yes, perfect. Okay, so now we're gonna ask ourselves, does this have any like cis, trans, easy, or chirality? No, there is no alkene here. So no, and there's no chiral compound or no chirality, I mean. Okay, so then we have to list our substituents. So right here we have a bunch of stuff going on at 4. We have 2 methyls, so that's going to be 4 dimethyl. And I believe that is all. So we just put it all together. It'll be 4 dimethyl hex 2 ine. And that is all. Okay. How are you feeling? We survived it. We did a couple problems. Go back to the other IUPAC naming workshop if you want more details on how that came together. But I say we should move on to just going over some things that are going to be on your test, because I know that's going to be pretty lengthy. Oh, let me see if I have it. Okay, I thought I definitely listed down what's going to be on your test, and now I can't find it, so that's a bummer, but let me try one more place. Sorry, 1 second. I could have sworn I had it out. I'll pause the recording while I look for it. That way you're not here sitting wasting. Oh my gosh, how do I even pause the recording? Here we go. Okay, sorry about that. I had to make sure that I was gonna talk about the right things. Okay, so now I got it. So the next thing I want to get into is hybridization. Just a really quick review. If you remember hybridization, it has to do with how many neighbors something has -1. And I remember that we talked about this very early into tutoring, and so into your class. And so we have what we like to call sp3, which is a tetrahedral. And if you remember the bond angle, it is 109.5 degrees. And it usually has 4 neighbors or 4 groups attached. Well, let's say 4 things here, right? 4 things. We have sp2, which is going to be trigonal planar. Trigonal planar, it is 120, and it has 3 things, right? And then sp, which is going to be linear. This will be 180, and it's going to have 2 things. So let's look at some examples of that. So if you were to get asked, what is the hybridization of, I'm going to say A, B, B. Of A, you would say, oh, this little carbon right here, it has 1 thing attached, which is this other carbon here. So 1 thing, and then it has 3 different H's, right? So I do 4. 1, 2, 3. And then this one. That is 4 things. It is sp3. So A is sp3. So all of the A's are sp3. So now let's look at B. B, so this carbon right here, how many things does it have attached? How many things? So it has one thing, two thing, three thing. We don't count these double bonds as separate things. It is just one thing it's attached to. So that is one thing, two thing, three thing. That is going to make B sp2. Remember, we always say things attached minus one. Do one more example before we move on. Okay, so the next example, it's going to be a little more complex. Okay, so let's see. I'm not gonna make you do all of these. Let me just make sure we get most of these. Okay. Let's see. We have. We'll do random ones and say this is A. This is B. This is gonna be C. D. E. Okay. A, we're going to count how many things it has attached to it. So we know it's one carbon, two carbon, and then it has two H's. So that's four things. So that's going to be sp3. sp3. Oh, we can hide this. sp3. Perfect. And then B has one thing attached, two thing attached, three thing attached. But this double bond prevents it from having a fourth thing, right? So he has one thing attached, two thing attached, three thing attached. So it's going to be sp2. Okay, remember sp3 is tetrahedral. sp2 is trigonal-planar. Let's look at C. This little carbon has one thing attached, two thing attached, three thing attached. So it's going to be also sp2. Let's look at D. It has one thing attached, two thing attached. So this little carbon right here, right? It's 2, 1, 2. So that's going to be sp, which is linear. Do you remember what sp2 was? Trigonal-planar. I had it right above too, right here. Okay, perfect. And now lastly, E. Let's look at E. This little carbon is going to be attached to one thing, and then it's going to have three different hydrogens. So that is a 4 things total. So remember, you have to always have 4 bonds for carbon, no matter what. So it changes. It has carbon can only have 4 bonds, right? And it must have 4 bonds. So whenever there's an alkene, you know that takes up already 2 of its bonds. So it cannot be attached to 4 things. It can only be attached to 2 things. And an alkyne takes up 3 of the bonds. So it takes up 3 and only leaves that 1 extra bond. So it can only be attached to 2 things. So that's when you know that's not going to be sp3 and that there's going to be a little change. E was sp3, and what is sp3? Tetrahedral. Okay, so that is it for hybridization. Let's move on to the next thing that your professor mentioned in his thing, which I noticed was radical stability ranking. Radical stability. And I think we only have like 5 more minutes left. thing about Zoom is that it doesn't let me do back-to-back meetings. It has like a buffer period of 20 minutes and I have to go into a meeting. So I won't be able to make the next video until like 11. But I will be able to make it, or I can text you to see if you just want to meet. I think meeting is faster. That way I know like where you're at. Okay, so radical ranking order. So a radical is a species with an unpaired electron, right? Unpaired electron. Stability increases with electron donating effects in resonance. So, unpaired electrons love being paired up, right? And so if it's just one lonely little electron, it needs that other negative energy from electron donating stuff. And so remember, if you're here and I'm here, if I have nothing around me and I feel so exposed, I don't have my blanket of electrons around me and I'm so cold, or I only have like half a blanket, I'm shivering, you're gonna come over and you having a big blanket is gonna help me feel more stable, right? Versus like if you also have no blanket, then we're not getting any stability. So I know it's a really crazy, wacky thing to remember, but remember, unpaired electrons, they are lacking something. So we want electrons near it. Stability increases with electron donating effects. And so the order of stability, so most stable would be a benzyl. Because a benzyl looks like this, right? And it has electrons going in a circle. It literally has electrons just going over and over and flipping around. And then the whole thing is just pretty, like has a lot of electrons, really stable. And so a little radical is here, let's put it here. It's going to be able to like have that energy and fill in that little missing piece that it needs. The next thing would be allylic. So that means little radical right next to an alkene. It's the same concept. It is right next to something that is very electron filled, remember, because a double bond means that there is more electrons being shared in the bond. Therefore, it has more of an electron presence. And yeah, okay. So allylic would be next, and then it would be tertiary, because more things around it would better be able to stabilize it. Then it would be secondary, and then it would be primary. So secondary, put H here. And then primary lastly. Okay, so most stable to the least stable. And then let's go on to radical and SN1. They're both very similar because SN1 requires a cation, right? It is a two-step carbo with a carbocation intermediate. A carbocation is literally missing electrons. So it is like a little positive gap. And so a radical and a carbocation have a lot of the similarity because they are missing that electrons, and they are trying to be surrounded by electronegativity things. So it would be the same thing. It would be tertiary, secondary, primary. And stability of the carbocation is key. So that stability is key. And so with SN1, you would want a tertiary carbon rather than a primary carbon because the reactivity is able to go by faster. Okay, I think I only have like 1 more minute left, but let me make sure. Oh, I have 2 more minutes left. Sorry, not 3. Okay, so we can go on and do the opposite, which is SN2. SN2 requires it's one step backside attack, right? One step backside attack in its ranking reactivity is from fastest to slowest. Oh, by the way, this is fastest, slowest, fastest, slow. So this is a different kind of way that it's working. So SN2 really requires it to have no steric hindrance, low or no, low steric hindrance. And so that means like moving things out the way. So no big bulky groups. So what does that mean? No big bulky groups. You're going to want a primary first, right? Well, initially you want a methyl. If it's just a little methyl floating out in space, out of the best. Then it's going to be a primary, then a secondary, and then the very, very least tertiary. Kind of no reaction ever happens in a tertiary. Okay, so the main thing that I want you to grab between radical and carbocation is that a radical, again, it is an unpaired electron. It is missing electrons. Same thing with carbocation, it is missing electrons. If it is missing electrons and it so badly wants to be stabilized, remember, stabilized means that it won't go into a reaction, that it won't cause crazy things. It is stable, it is happy, it is good. If it wants to be stable, happy, and good, if it's missing electrons, if it's missing electrons, then it's going to want electrons. What has electrons? Double bonds. This has 3 double bonds as opposed to 1 double bond. This has 1 double bond opposed to nothing. But this has more things around it. Because remember, H provides no electrons, and H is a proton, and H has literally no electrons. And so if it has more H's, a radical is going to be very sad. Less H's, a radical is going to be okay if it has more things going on. Okay, I think we have to go. I will see you after my meeting. Let me know if you have any questions. Text me if you need to. I'm going to try to upload this YouTube video. All right, bye-bye.